Hey guys, welcome back to the second part of topology. Today we're going to talk about continuous functions. In the last video someone brought my attention to the low visibility of the blue writing, so I switched to a brighter color. I hope that the readability increased now. Let's start right away with our first definition. 1.3 Continuous functions. Let x dx and y dy be a metrical space. A function f is called continuous in x0 if for all epsilon greater than 0 there exists a delta greater than 0, so that for all x in x which have a shorter distance than delta to x0, the distance of f of x0 to f of x is smaller than epsilon. What that means is that f of x can be arbitrarily close to f of x0 if x gets close enough to x0, as you can see in the little graphic I made here. We call f continuous if f is continuous in every x0 in x. Let's look at some examples. 1.4 Examples of continuous functions. First, constant functions are always continuous, the identity is continuous, and if f and g are continuous, then f plus g, f times g, and if properly defined, the composition of f and g are continuous. The composition of f and g is just g of f of x. And for the next part of the lecture, our goal will be to try and find a definition of continuous functions that will not require us to operate in a metrical space, but will rely on a more abstract structure, the topological space. And for that, we are going to have another definition, open epsilon neighborhoods, 1.5. Let x be a metrical space, x0 element of x and epsilon greater than 0. Then we call b epsilon of x0 the open epsilon neighborhood of x0, where b epsilon of x0 is defined as the set of all x in x which have a shorter than epsilon distance to x0. You can see a little example in this graphic I made where epsilon is 1/2 and x0 is the point 1,1. So this would be the open 1/2 neighborhood of the point 1,1. A general neighborhood of x0 is a subset U of x, so that there exists an epsilon greater than 0 with the open epsilon neighborhood of x0 is a subset of U. Then we move on to the next definition, which will be our motivation to move beyond the limit of metrical spaces and develop a more general framework in which continuity will still make sense. 1.6 Open sets. Let xd be a metrical space. U subset of x is called open if for all x0 in U there exists an epsilon greater than 0, so that the open epsilon neighborhood of x0 is a subset of U. This means that U is neighborhood of all its points. Let's look at an easy example to make this definition a bit clearer. As the name suggests, the open epsilon neighborhood around the point x0 are open. This is because for any arbitrary point x0 in it, we can choose delta as epsilon minus the distance of x to x0, as you can see here. Then, the open delta neighborhood of x is a subset of the open epsilon neighborhood of x0. Because we did this for an arbitrary point x, this means that the open epsilon neighborhood around x0 is open. To finish this lecture, we are going to prove a theorem. 1.7 Theorem. Let xd be a metrical space. First, the empty set and x are open. Second, let J be an arbitrary index set. For a family of open sets in X, Uj, the union over all J, Uj is open. Which means you can take arbitrarily many open sets and unite them, and the union will still be an open set. Third, let U1 to UN be a finite number of open sets of X. Then the intersection of U1 to UN is open. So this means you can take a finite amount of open sets and the intersection of these sets is still going to be open. Okay, let's prove this. Starting with the first point. The first point is basically true trivially because openness is a property of a set that only concerns its elements. So the empty set is open per default since it doesn't contain any elements, hence the property holds for all its elements. And x is open because for every point x0 in x, every open epsilon neighborhood around x0 is a subset of x per definition of open epsilon neighborhoods. Thus x is open. The second point is where it gets a bit more interesting. Let x0 be an arbitrary element of the union of all uj. That means there exists an I of j with x0 as element of ui. Because ui is open, that also means that there exists an open epsilon neighborhood around x0 that is a subset of ui, as per definition of openness. But if this epsilon neighborhood is contained in UI, that means it's also contained in the union of all UI. Hence, the union of all UI is open. And then to the last point, let x0 be an arbitrary element of the intersection of u1 to un, then x0 is element of every uk for k between 1 and n. Since all the uk are open, that means every uk contains an open epsilon k neighborhood around x0. Now take the minimum of all these epsilon k's and set it as epsilon tilde. Now the epsilon tilde neighborhood around x0 is a subset of all epsilon k neighborhoods, which further means that the epsilon tilde neighborhood is subset of every uk, and thus the epsilon tilde neighborhood is subset of the intersection of all uk's. It follows that the intersection of all uk's is open, and we are done with the proof. You can see a little visualization that explains why the epsilon tilde neighborhood is a subset of every epsilon k neighborhood. If you didn't quite get it before, I recommend you to just pause the video at this point and study this graphic. This should make it a bit clearer. So yeah, that's all for today. And here, watching and subscribe if you don't want to miss the next part of this series.